Left off talking about Huffman Coding, which is the second part of your assignment due this Friday. We left off with me showing you how you could do it, do a one-liner where you would get the character counts from the file pretty easily by just opening up the file and then doing a map comprehension. So let's remind ourselves how it works, first of all, that you're iteratively building this tree. Right, that you start out with the lowest frequency characters and you start combining those. Each iteration of the algorithm, you combine, all of these trees are in some sort of data structure, right? We started out with just the leaves here, and then we iteratively combine them. We combined the two lowest ones until we were down to just one big giant tree here. This was one, that was one example. This is another example. In fact, you can make a combinatorial argument that there are an exponential number of equivalent trees. All you have to do is take any internal node here and swap out the left and the right child, and it would lead to a different code, but it would still be prefix free. It would not change the depth of any of these nodes, and so you would end up with the same code word. You'd end up with the same compression ratio here, okay? So when you go to program this, you know, if you want to put the lesser one on the left and the greater one on the right, if you want to randomize them, it doesn't really matter. Okay, it's easier to program it and be consistent about it, but your choices don't matter. It'll lead to an equivalent code. For that reason, the expected output might be a little bit different, but your compression ratios will be the same. Okay. All right, so how do we go about actually implementing this via pseudocode? I'm just going to jump right into the pseudocode here. Let's see, where is it? Here's the algorithm. I won't bother revealing it back and forth. Instead, let's just go ahead and annotate this, okay? This algorithm right here, it just builds the tree. Once you have the tree, you still need to build the code, right? If you have the tree, what could you do? You could start at any leaf, and then you could traverse it back up to the root and then reverse it, 0, 0, 0, 0. Right? Or you don't even have to reverse it. That could be, because that's going to be an equivalent code as well. Or you could start at the root and then do a pre-order traversal. Right? Anytime you go down a left child, you append a 0. Anytime you go down to the right child, you append a 1. When you return back up, right, then you take off the last bit in the string that you're creating here. Right? When you hit a leaf, that's when you output the code for that leaf right there, F, right? Okay. This algorithm builds the tree, right? We take as an input an alphabet of symbols, right? A sigma here with relative frequencies, right? So that could be a percent, 15%. It could be a character count. It really doesn't matter. You're still minimizing things, okay? We say sigma here because, again, if you pre-process the file and you find that there are no Z's in it, there are no capital Q's in it, then throw those out. Those are not part of your symbols. You're not going to encode any of those. Right? Our output here is going to be a Huffman tree. Cool. What is this thing right here? A Min Heap. Right? Ignore the rest of the algorithm for a moment here. Why would we want a Min Heap? Let's go back to our process over here, right, where we put all this stuff together. What was I doing? I was pulling out the two minimum frequency nodes at any one point. Once we combined those, then we had 0.8, and then the other smaller one was 0.12, combining into 0.18. So I need a data structure where I can put stuff in, and I can take out the minimum element, and then I want to find the next minimum element, take that out, combine those into a new tree with a new frequency, and then put it back into the data structure so that next time I ask for an element, I get the minimum element. Why does a heap give me that property? What is it? What is a min heap? We'll look at this in detail, but this is review. What is a min heap? It is a tree data structure that offers two basic operations, right? Get and remove min. This is for a min heap, right? And you don't have arbitrary access to anything that you want. It's not a binary search tree where you're searching around for a particular element. Instead, you just want to put stuff in, And when you take stuff out, you want the minimum element. So put stuff in would be add, right? Add an element to the heap, right? Those two basic operations. Do you remember, say, from computer science 2? Both of these operations are going to be what? Order what? No? Nope, even better. Oops. Log n, right? Where n is the size of the heap, right? We'll come back to this because we're going to review heaps here in a second. But this is why we want it. We've got these two instructions, and it's super efficient to do each one of them. Okay? We'll come back to that. I create a new heap here, and then what I do is for each element, for each symbol, I create a new single tree node, just like I did over here, right? I created each one of these single node trees, right? Seeds, if you want, okay? And then I associated with them the symbol and also the weight, which is initially the frequency. And then I put that tree node into my heap so that when I take them out, I'm pulling out the minimum frequency ones at, first. Yeah.
Is there like a heap in Python?
We'll look at that in a second. All right. All right. While the size of the heap is greater than 1, right? While I'm not down to the to the last element, right? Once I've combined all the trees and I've got one tree remaining, I break out of this while loop and I return that tree. Okay. That root node. Okay. That ultimately gets returned right there. Now, I think you asked yesterday, well, how do you do different nodes? You don't, right? Each node contains a character. Node would contain a character and a frequency or a count or whatever, however you want to do it. And for the internal nodes, this would end up being none for internal nodes, right? These nodes right here. Otherwise, it'll be E. And then that way you can tell, is this an internal node or not? Okay. All right. Let's focus on the main loop now. I create a new tree node. Right? That, remember that I had those two elements, and then I'm going to create a brand new tree node here. And that's going to be my new root. Then I go and get the minimum. Right? I get and remove the minimum. I get and remove the second minimum. That's going to be T sub A and T sub B. I end up making those the left child of this new root and the right child of the new root on these two lines. And then what about the weight of this new root, this new tree node? That's going to be the weight of this one plus this one. And that's the weight of that internal node, right? That's it, right? It's exactly what we did visually on Monday. Then I put that tree back into the heap because I'm putting it back into the collection. Right? Now, where it ends up in the heap, who knows? Who cares? Because next time I ask for something, I'm only asking for the minimum. Okay? So before we look at the details of heaps again, let's analyze this. Okay? Let's look at this phase first of all. What's the elementary operation? Like creating a tree node, sure. Creating or associating with it a weight, okay, you do that. But what's the most expensive thing? Probably inserting something into a heap, okay? So now let's think about this. How many times do I do this for each X in the set of symbols? This loop is going to run for how many times? I guess I didn't state it, but let's suppose that it's n, right? Where the size of sigma is n, okay? The cardinality of that set. I'm going to insert each one into a heap, but you have to be careful, right? The cost of heap insertion is going to be, as we already said, I'll take out the order, and I'll just say that it's log n. Except that that's not our n. Right? Let me give that something else. Log m, where m is the size of the heap. Now let's think about this first loop here. The size of the heap is changing. Right? On the first iteration, the size of the heap is 0. Now log base 0, is that defined? Or log base 2 of 0, is that defined? If you're in calc, it is. Well, what is it? Something like that. Is 0 defined? It's going to be negative infinity, right? That's not what we want, right? So what is the complexity here? Well, you end up doing no comparisons at all. Why? Because if you have an empty tree, how do you insert something into a tree? You just make it the new root, and that's it. All right? On iteration 2, the size is now 1. So the complexity is going to be log of 1. Right? Okay, about. Again, I'm ignoring the fact that I've erased that big O from this thing. Okay. On the next iteration, 3, it's of size 2, and so it's about log of 2. 4 becomes a size 3, and it's the complexity is log 3. Right? Dot, dot, dot. On the ith iteration, the size is going to be I minus 1, and therefore the complexity is going to be log of I minus 1. The last iteration is what? N, because I go over n elements here, right? Order n here. Okay. And the size is going to be n minus 1, and so the complexity of inserting that guy is going to be n minus I. Or, sorry, what am I saying? N minus 1. So, sum these up for me. Oops, come on. Copy. Paste. What is the grand total here? Okay. N? So the total sum is going to be log of 1 plus log of 2 plus dot 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 log of n minus 1. You can go ahead and throw in the last log there if you want to. Right? Plus log n. There we go. It'll look nice when we do this. Right? Right, remember it's big O, so this is actually less than or equal to. All right? Apply your log identities. Log of A plus log of B is equal to what? A times B. Do that for 1, 2, 3, 4, 5, all the way up to n minus 1. And what do you get? 1 times 2 times 3 times dot 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 times n. That's why I went up to n, so it's nice and round, right? And that's going to be equal to, like you said, log of n factorial. Now you can pull out a tool called Stirling's approximation to get a continuous version, a continuous approximation of n factorial here so that you can play around with it. I'm not going to go that far though. Make it bigger. Log of n to the n. Right? That inequality holds, right? Why? Because 1 times 2 times 3 times 4, all you need to do is make each one of these bigger. N, dot, 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 n. N times n times n, how many times? N times is going to be n to the n. Now apply another log identity. What can we do with that, what can we do with that exponent there? Bring it down. N log n. Hey, cool. That first one is going to be n log n. Not necessarily linear, but almost quasi-linear. That was only the first loop right here. But guess what? We are getting the minimum, which is going to be, again, be each one of these things, each one of these operations, but twice over. And then you have to realize here that you're going down in size, right? You are decreasing the size, and so what ends up happening is in the second loop, you end up with the same exact thing, but in reverse, right? And since these are both, separate loops, they're not nested or anything, This is going to be ending up being n log n, which of course is n order n log n. Very, very efficient. Okay. So there's our analysis. In fact, it's the same analysis as you would do with like heap sort or something, right? Now let's remind ourselves what are heaps again, right? Hopefully we're kind of remembering it now. If not, that's fine. Where's my heap? Here's a min heap. Okay. So what is a min heap? A min heap is a binary tree. It can be viewed as a binary tree, such that, tell me about the children. Any one node here, both of its children are going to be greater than it. Greater than or equal to, and greater than or equal to. It's not a binary search tree. If I'm searching for 65, or let's go with something. Yeah, let's search for 65. Right? Would that be successful? Okay. Well, you need to go right. 65. Oh, that's greater than 30, so I need to go right. But I missed it. Where is it? It's over here. So the same operations don't apply to a heap. The only two operations that actually are supported by a heap that are efficient are get min and add. Okay. So how are those? So one property first of all. Tell me where the minimum element is in a min heap. Yep, all the way at the root. Okay. How do we end up doing these two operations? How do I get the minimum, get and remove the minimum, and add an element? So let's think about getting the minimum first of all. Right? Well, first of all, what can I do? I can say, well, it starts immediately at the root here. So save off 1 so that you can eventually return it. But the problem is, how do I remove it? If I just remove it, I've got a gap here, right? So one thing that you might immediately think of is, well, you could promote, say, 5. Maybe you could bring 5 up here, right? Okay. Except that now you have a gap right here. Oops. I want that. There we go. Now you have a gap here. Which one can you promote up now? 50. Oops. Too thick. 50. There we go. And now you've got a, come on, not thick enough. Now you've got a gap here. Which one can you promote up? 53, because it's a min heap. You want the minimum to be smaller than both of its children. Okay, good. 53 is up here now. Uh-oh. Now what? We have this gap here. A heap has to be full. Its entire entire basis of its complexity, that this is efficient, relies on the fact that it's a full binary tree. That every single level has all the nodes except for possibly the last level, and they're all packed to the left, right over here. Okay. So that kind of sunk us. So I'll save off 1. And I will delete it, but I shouldn't promote its children. Remember that there's this fullness property where everything needs to be here except for possibly the last level, and it's all to the left. I should ensure that that property is still satisfied. So which one could I promote? 63. So, and because it's a leaf, what can I do? I can just delete it. 63 comes up here. Ah. Right? Damned if you do, damned if you don't. 63. Is this a min heap anymore? Nope. It's okay. Why? Because now that you've satisfied the fullness property, you can go ahead and swap things out. Right? 5 and 63. Right. Now, is this a min heap still? Nope. 63 is greater than both of its children. So what do? Swap with its minimum child. Right? So now 50 is up here, and 63 is down here. Is that a min heap? Nope. So we do it one more time, 63 and 53, and now, if you draw it a little bit nicer, and now it is a min heap. That's called heapifying. You heapify it down. What would it look like if we wanted to insert something? Right? Yeah, let's start with a clean tree. There we go. What if I wanted to insert something? I don't want to make the same mistake of starting at the root. Instead, what I want to do is I want to start at the bottom. Let's say that I want to insert, I don't know, 3. Insert 3. I want to make sure that that fullness property is satisfied first. So I insert it at the next available spot. Right? The fullness property is now satisfied. But is the heap property satisfied? No. We do the same trick upwards, though. We heapify it up. And this becomes 53. 53. This becomes 3. The fullness property is still not satisfied, so we swap these. 50. And now this is 3. Right? The fullness property is still not or the heap property, excuse me, is still not satisfied, so we swap these. And now it is satisfied. Right? The fact that it's a full binary tree means that the depth is guaranteed to be logarithmic. Both of these operations are proportional to the depth of the tree. Therefore, both of these operations are order at log n. Right? Great. All right. So how do you go about implementing a heap? Here's the trick. Actually, no, let's use the same heap here, min heap. Right? And what I'm going to do is I'm going to go ahead and put them into an array. There we go. 0, 1, 2, 3, 4, 5. I won't be too fancy here. I'm going to burn the first one so that it looks nice. All right? Don't worry about this. Otherwise, what I'm going to do is I'm going to go in a BFS manner. Top to bottom, left to right. It's all contiguous because it's a heap, right? They're all together. So each one of these is going to be in its cell, right? 1, 5, 30, 50, 55, 6, 7, 8. I'll do a few more, right? 55, 40, 80, and the next row is going to be 60, dot, 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 dot. Now, why does that help me? It's because of how the indices work. There we go. If I have an element here, u, at index I, then its left child is going to be at 2i, index 2i, and its right child is going to be at index 2i plus 1. And all you have to do is reverse that to find its parent. It's going to be at I divided by 2 floor. Right? See that at work over here? Let's go ahead and consider 40. 40. Let's go with 30. Where is its left child? Well, if it's at index 3, then its left child is going to be at 3 times 2, which is 6. Hey, cool. Where is its right child? 3 times 2 plus 1, which is 7. Right there. There's its left child and its right child. What about its parent? 3 divided by 2 floor, which is going to be 1, which goes back to index 1. Cool? Again, here's the visualization with a different heap. Here we go. There. Right. All you have to do is start at any index here, jump forward 2i, jump forward 2i plus 1, or jump back by a floor. Okay? All right. So now let's think about practical implementations for this Friday. I want a heap. Should I go and start coding my own? Probably not. Nobody likes to start from scratch. Right? So, tell me about heaps in Python. Import heap q. The q stands for queue. like literally a queue, a line, Q-U-E-U-E, right? The heap, why? It's because heaps are priority queues. A priority line, right? That when you've got a line of people, right, it's first come, first serve normally, unless they've got a priority, right? Somebody gets to jump ahead of the line, and you always say, all right, I'm serving the next priority next, right? That's not necessarily the next person in line. I mean, it is because they're at the head of the line, but then this person doesn't get served next. The person with the next priority, highest priority, gets served next, all right? It is a min heap implementation, but it doesn't actually use any special data structure. You instead heapify arrays. Actually, lists. We're in Python. There are no arrays, right? Lists. Okay. What do I mean by that? Well, let's go ahead and create a list here. I'm just going to call it H, short for heap, right? In fact, I think I stole this from the documentation. Right. There we go. Is that a heap? Let's draw it out. Yeah, there we go. So if we were to treat this as a heap, top to bottom, left to right, the root would be where? 1. Make it thicker. 3, 5. Looks like a heap so far. 7, 9. Yeah, that's heaping, right? Uh-oh. 2, 4. There we go. We have our first counter example, right? 2 is a child of 5, which is less than 5, and so this does not have the heap data heap property. 4, 6, 6, 8, right? 0. There we go. So what we need to do is we need to fix this heap. It's not a heap. We need to make it into a heap. Heap q dot heapify, right? That's exactly what it's called. It's heapify it. Make it into a heap, right? Let's print it out and see what it looks like after we're done with that. Python demo. There we go. All right. 0, 1, 2, 6, 3, 5, 4, 7, 8, 9. It's only slightly different. It only fixed those few that needed to be fixed, right? So let's take a look at what it looks like now. Sorry, I should have. There we go. So 0, and then the left child is going to be 1, 2, 6, 3, 5, 4, 7, 8, and the last one is 9. There we go. 9. That looks a whole lot better, right? The min heap property is satisfied. It's all contiguous. It's been successfully heapified. All right. Now, what can we do with it? We can treat it like a regular old list. We can search through it. We can append to it. We can do whatever we want. But if we want to maintain that it's a heap, we need to make sure that we're using the interface. So heap q dot push and pop. Heap push and heap pop. Heap q dot heap pop. There we go. Those are the two functions that you'll probably want to pay attention to. If you're pushing something, you're pushing something onto the heap. Let's push 42. That's going to be greater than everything, so where is it going to end up, by the way? If I inserted 42 here, where would it end up being? 3's right child, I agree. If I ended up inserting negative 42, where is it going to end up being? The new root, right? 42, and then this stuff gets heapified down somehow. Let's see how it works. So if you push those two things in that order, then let's go ahead and print it out. And I will ignore that for a second. Right. 42 is now at the beginning, right? 1, 0, 6, 3. If you were to write that out, you would find that the heap property is satisfied. 5 actually ended up getting heapified down or something, right? Right? Something like that. Okay. Okay. Heap pop gives you the next available element. So if I print out x here, it's going to pop out the minimum element, which is 42. Oops. Heap pop takes a, oh, sorry. You have to give it, it's not object oriented. You actually have to give it the heap, the list that you're that you're treating as a heap. And there we go. Right. Negative 42. If I were to print this again, again, it's removed that element. It's removed the the minimum element. 42 is now out. You popped it out. You're pushing stuff in, you're popping stuff out. What if I wanted to do this all the way until I reach the end? While heap, or H, pop it out, print it, and be done. Why does this work right here? So negative 42, 0, dot, 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 dot. It's sorted, right? It all pulled out in a sorted manner. Why does this syntax in Python work? While a list is true or false. It's called truthiness, falsiness, right? When is a list true? When there's something in it. When is a list false? When it's empty. Or another situation in which H is equal to none. Won't do anything. Why? Because none is false. Right. Don't do that. There we go. So, how would you go about implementing this stuff? Just any sort of tips or tricks that you want to hear about for this? Well, the first step is probably going to be, well, stealing that code that I gave you on Monday to compute the relative frequencies. You're probably going to want to design a tree node that holds a character and a weight, so that you can update those. For internal nodes, that character is going to be none. Right? For weights, when you combine two things and make one a left child and one a right child, you need to make sure that you set the weight up here to be the sum of those two weights. And then you're going to put it back into the heap. That begs the question, though. This was a heap of integers, which is pretty straightforward, right? What would a heap of nodes look like? Are you going to be able to put in arbitrary objects? Let me show you. How do I do a class? Class, foo, and I'll just say x, let's see, what is it? Func, or no, it's define, init. Is this right? Oh, not this, self, there we go. And I will just say take A and B. There we go. And so self.a is equal to A, self.b is equal to B. Is that the correct syntax? Oh, here. I'll ask the interpreter. Is that the correct syntax? It looks like it is. All right. So let me go ahead and create a new heap here of nothing. And let me create two new foos, right? X is equal to foo of 10 and 20. And Y is equal to foo of 20 and 20. Something like that. If I put those into h.append, actually no, let's go ahead and treat it like a heap. Heap q dot heap push hx, and then I'll put also y into that. Is that going to work? Nope. You know, well, it is heapified, right? An empty list, by definition, is a heap, right? Empty anything is true, right? But vacuously true. It's going to complain about this, I'm sure. Wait a second. I don't know how to compare foos. When I got two foos here, and I want to put the first foo in, and I want to put the second foo in, how do I know which one goes first? Yeah, you need a comparator, right? So Python comparator, not comparator function, comparable class. How do you make a class comparable? Right? Comparable classes in Python 3. Right? There we go. So you can use func tools, total ordering, and all you have to do is define at least two functions. You have to, well, here, the post is a little bit more succinct here. you have to define LT and EQ. What do you think those stand for? Less than and equals, right? So then it can answer the questions of, I've got two foos, which one goes first? Right? And all you have to do is make your, is bring in this, this tooling. This is one option, by the way. There are many other options. Bring in this tool, define these two functions for your node, and suddenly the nodes become comparable, and you can use them in a heap data structure. Right? Yeah,
You just make tuple.
that's the other solution. I don't like the foos. I don't know what foos are. All right. So what you can do is you can go heap push, and instead of pushing just x, a foo, which is x, you can push a tuple, 10, 20. And you can push this tuple, 20, 10. Right? And that will work. Python is perfectly happy about that because if it sees a tie, 10, 10, then it goes to the next thing in the tuple to break a tie. The gotcha there is that you have to be able to break ties, right? That eventually you are going to want to put a node in here, right? That other foo, x and y, right? And x is equal to foo of, I don't know, 20, 20, and y is equal to foo of 30, 30. Right? This will work as long as something, oops, not y. There we go. Sorry. This will work. Why? Because it looks at the first thing in the tuple and says 10, 20. I know what those are. Those are integers. 10 goes before 20. Right? If you have ties, 10, 10, okay, I need to go to the next thing in the tuple. 10, 20, okay, I know what those are too. And 10 comes before 20. But then if there are absolute ties everywhere, right? Then it goes to the third one, x and y, and then we're back at square one, where we don't know how to compare foos. Right? So you might as well start off doing this anyway. Right? Or the other solution is, so question, if you go with tuples, what should they be? What tuple are you going to want to represent a tree node over here? You're probably going to want a node, definitely. But what other information do you need? Come on, where is it? There we go. The character, the frequency. All right. Yeah, go ahead.
So like when they come into there's a duplicate when the frequency is the same. They have more fun.
Exactly. Exactly. Right. So the first one you're going to want is the frequency because you want it to work. The second one, you want that to be your tiebreaker. What's guaranteed to be unique? Characters. Right? Characters being, character. And then maybe the node. It looks like it works at first, but eventually you're going to be combining internal nodes. Do internal nodes have characters? Nope. So instead of having none, which is not comparable, you may want some dummy string instead to break ties. Right? Like given, if we had something like this, what if the frequency was, I don't know, it appeared 10 times and there was no character, but there was a node, some node. All right, there we go. Another frequency was 10, none, and some node. We want to combine that. We want to put those into the heap so that we can pull them out and combine them with a new node, right? Some other node. All right. What's going to happen? 10, 10, same. None, none. You may not even get past the none, so be careful, right? And then, of course, then it would go to the foo, and you would be back at square one. So again, what's the easiest thing going to be? Just get it all done to begin with this. Right, make sure that it's a total order. Yeah.
Well, what's inside the node? Is it just the same thing as?
Well, I mean, it'd end up being what?
The character.
Frequency and character. Yeah. There you go.
So even though the node has the same, maybe two nodes have the same frequency and character, you do two different ones.
Well, two nodes could have the same frequency and different characters unless they're internal nodes. Then they could have the same frequency, the same missing character, right? And you need to be able to break ties like that, right? So you need to have a total order. That's why it's called func tools total ordering, right? You might remember, say, from 235, partial ordered sets. Partial ordering is when you've got reflexivity, transitivity, and, do you remember? Antisymmetric, right? So, but you've got things that might be incomparable. A is less than B. B is less than C. But D is not comparable to any of them, right? It doesn't fall. So it's not less than A. It's not comparable to A. It's not less than B. It's not comparable to B. You could put it anywhere if you want, right? To impose a total ordering. You could say A, B, C, D. Or you could say D, A, B, C, right? Or you could say A, D, B, C. And that would all be compatible with your partial ordering. Do you remember the algorithm? Hopefully you went over in 235. The algorithm to take a partially ordered set and turn it into a total order. It's called topological sorting. Right? Yes? No? I heard it somewhere. Okay. This pops up all over the place when you go to sort something. When you create a user-defined type and you want to sort it, you need to make sure that it's a total order. Because how do you sort two things that you can't compare? I've got two foos here. Well, does this one come first or does this one come first? And when you try to do that without specifying, you get stuff like this. I don't know how to do that. You need to tell me how to do that because this is a user-defined type. It doesn't need to be told how to do that with integers because those are built in. It knows how to. It knows that 5 comes before 10, right? So you don't have to worry about those. Yeah.
So it needs to have some kind of tiebreaker.
Yeah, you always need a tiebreaker. Yep. This pops up in databases all the time too, right? This is why you design a database with 3 normal form, so that everything is uniquely, like you could have an entry where you have the same first name, same last name, right? And maybe your tiebreaker is a social security number, right? Because that's supposed to be unique, right? It ain't, right? Because a social security number could be, it could be identity theft, right? It could be that they mistakenly issued the same social security number. It's unlikely with social security numbers, but it happens sometimes with NUIDs, right? Social security numbers you also run out, right? And after, I believe, somebody's been dead for 50 years or something, they can recycle that number and reissue it to somebody. So over time, they're not unique. This is why you design databases with primary keys that are auto-generated, guaranteed to be unique, right? You always have a tiebreaker.
So do we do something like a primary key or node ID?
I don't think you need to, but you could. Again, the tiebreaker is probably going to be the character, and then for internal nodes, you'll have to figure something out. One thing that you could do is you could inherit, not inheritance as in like object-oriented programming, but one practical thing that you could do is say, well, this internal node, it doesn't really have a letter associated with it. Here, let's go down to this one. This one doesn't really have a letter associated with it, but for the purposes of Python that needs a way to associate it, we'll go ahead and promote one of them up, right? So that there's, an implicit D here, right? And that doesn't matter either. G, D, it doesn't matter. That this tree is associated with G, so that this tree ends up getting associated with, say, A. And this tree, the A and F, right? Then there's your tiebreaker, right? So it could be none for internal nodes, or for practical purposes, you could promote that up and just reuse it. Right? You could do the minimum, right? You could do a concatenation, because that's what you do here. You sum them up, right? So you could just do a string concatenation, and that's the string associated with that, right? That's guaranteed to be unique, because if it's not, then you don't have a prefix-free code, right? So there are lots of little things that you could do to do something like this.
So if
Yeah.
we do that, can we use tuples?
You could. Again, I I think you're gonna bringing this library and playing around with it. You'll really appreciate it. I mean, in Java you use the comparable interface. This is how you do the comparable interface with Python. You only have to write 2 functions. It will automatically inject or infer. The library itself will automatically infer all the others. Why don't we have to write greater than, right? Well, greater than is not less than, right? And not equal. That's why you need 2 of them to be able to distinguish it. Right? So it's able to determine, it has default values for all the other ones as long as you do at least 2. You could do greater than and equal if you want to instead. Or you could do all of them, right? And go nuts. All right. Yeah. Mm-hmm. Yeah, the character ASCII values, yeah.
How would you guarantee that like one person on a tree is going to be less if it's not?
Well, you only look at the root of each subtree at any one time, right? And if this one is associated with A, and you were comparing it with this tree over here, A is already in this tree. It would never appear in this tree. Therefore, it would never appear as the representative of this over here, right? I mean, you always go with the frequency first. But if you've got a frequency of 0.39 and 0.39 here instead, you just need to make sure that A and, I don't know, maybe B over here, right?
So if you promote F on the left and then like C on the right, wouldn't C come out as less than F?
That's okay. F, C, that just means that you switch these children around, which gives you an equivalent code, different code, but equivalent with the exact same compression ratio. Right. In fact, I when I was running this morning, I retroactively thought of the next problem I'm going to give next year is given a Huffman tree with n leaves. 1, how many internal nodes does it have? And 2, how many equivalent codes are there? Right. So the really quick answer here is you introduce an internal node on every iteration of the algorithm. How many iterations are there? n-1. For each time you combine them, you can put one tree over here, or you can put one tree over here. Or you can swap them around. Therefore, you have 2 choices for each iteration, 2 to the n-1. There are an exponential number of equivalent codes that achieve the exact same compression rate. And now, I don't know if I'm going to do this course next year, but if I do, and somebody does all the digging, they'll find the answer. But if they did that much digging to find this video, then good for them. All right. Any other questions? Okay.